Okay, so far in our little study of electronics, we have been looking at what is known as DC circuits. So DC circuits stand for direct current. So basically the current moves in one direction. We've talked about it going from the battery's positive terminal to the battery's negative terminal in a single direction. There's another kind of current, actually what we use in our usual household or generators, and that's what's known as AC current or alternating. And so I'm going to give you a little introduction to alternating current, and I'm going to do a practice problem working, of course, with the information. This is the type of current that we have in our household. We talk about our household current being 120 volts at 60 hertz, whereas current in Europe is different. And so we're going to talk about how we use the ideas of AC current with the tools that we developed for our DC. All right, let's take a look. So current alternates from a generator in a sinusoidal fashion. And so let's just remind ourselves what that means. That means that it's a sine wave. All right, there are a couple things about a sine wave that we know are important. One is the frequency of that sine wave, so how many cycles we get per second. Now, as a reminder, if you want to go back and kind of look at simple harmonic motion in Physics 1, might have been the first time that you looked at this type of behavior. And then, waves, sound waves, wave behavior might have been another time. Same principles in terms of the peaks, okay, and in terms of the averages we're going to talk about, and the timing of that wave, in this case, the frequency. So like I mentioned, the frequency, the number of cycles per second, that is in the US, we talk about it as being 60 hertz. So just as a reminder, those numbers that you might hear when you look at the back of a battery, at a plug, it talks about both voltage and a frequency rating. So those are the frequencies we're talking about. All right, if we're looking at the voltage per time that's produced from a generator, a sinusoidal function is given by the equation voltage is equal to V naught, we'll talk about what that means, times the sine of 2 pi, the frequency, times time. And this is also written as V naught sine omega t, where omega is equal to 2 pi times frequency. Right, again, that frequency is that cycles per second as time goes on. Now, V naught, that's our peak voltage that the generator produces. And V naught oscillates between positive and minus. Okay, so V oscillates between positive and minus. All right? Now, Ohm's law still applies in our ohmic devices, right? We're still dealing with different types of resistive elements that produce power. So Ohm's law still applies. And remember, as a reminder, Ohm's law, V equals IR. Well, now the resistance is a property of that element. Remember that whole discussion of resistivity. So go back and check out those videos if you're not sure, like, can resistance change? We can have variable resistors, but we set them to a single value. So if the voltage is oscillating, but resistance is a property of the device, that means that the current, you probably clued into that, the current is also oscillating. And it oscillates in the same way as the voltage. So remember, the current is equal to V over R. So if the voltage is oscillating, I'm just going to pop this out, 1 over R, okay, and V naught sine, I'm going to use omega t. Okay, so 1 over R, V naught sine omega t. Sine omega t. Well, I can define I naught as equal to V naught over R. This should be a capital R, sorry. I can assign I naught, the highest current value to be the highest voltage value over the resistance. That should make some sense. So now when I substitute that in, we have I naught sine omega t. So the current in an AC circuit oscillates between a peak current that is defined by the peak voltage and the resistance. So these are the two relationships for how AC currents work. Maybe as I was introducing this and I alluded to some things about, like, this is the type of voltage that we get in our household. But if I look at, like, on average, what's the average voltage that exists? Well, on average, the average of a sine wave is 0, which means that the average voltage over time is 0. Similarly, the average current over time is 0. So how do we get power to anything? Well, we want to look at the power relationship. So how do we, I'm going to put these down here so we have them. So we have V is equal to V naught sine omega t, and we have I is equal to I naught sine omega t. All right. So let's look at power, because, I mean, if I have an average on 0, how do I get anything? Does it mean that there's no power to these elements? Well, we, of course, know that's not true, so let's look at how that works. To do that, we have to remember what the power relationship is. And the power relates voltages and currents and resistors also, right? Using the ideas of Ohm's law and power being energy per time. Go back to that power video if you want to review the ideas about power. But if I look at the power relationship as it relates to current, power is I squared times the resistance. All right, so if I'm alternating, I still have my R, that stays, but now I have I naught sine omega t, quantity squared. So I squared R, which is, I'll keep the R on here, I naught squared sine squared omega t. And we often see this written as I naught squared R sine squared omega t. So these are identical. I thought that might be easier to kind of review it that way. So what does that tell us about power? Well, power is a function of sine squared. And sine squared, that's always positive, right? So if I square the sine function, sine squared is always positive. So our average power is actually positive. Our average power is positive. And so if I take the average of this function, our average power is equal to 1/2 I naught squared. All right, that's times R, of course. Sorry, times R. So this is the average power, which is always positive. So that's a good thing. That's how we can kind of appreciate that these resistive elements get power, right? Dissipate power. Okay. This is the relationship, of course, in terms of current, and you can do the same process. The average power can be related in voltage as 1/2 V naught squared over R. Okay. So just our power relationships depending on resistance. So power, you know, is IV, but it is also I squared R or V squared over R. Okay, so what's important for power is the current squared and the voltage squared. That's what's important for power. The average current squared, okay, the average current squared is equal to 1/2 I naught squared. Okay, so on average, the average current squared is equal to 1/2 the maximum squared. Okay, so on average, the average current squared is equal to 1/2 the average squared, and similarly, our average voltage is equal to 1/2 V naught squared, okay? So if I take the square root of both of these, so take the square root of this relationship, which of course takes the square root of this relationship, we find that the average current, we get some relationships telling us the average current is I naught over the square root of 2, and the average, velocity, I'm going to hold off that for a second, is I naught, not I naught, certainly not I naught, V naught over the square root of 2. So this value, we have a name for this value. I'm going to rewrite it as about 0.707 I naught, and this is about 0.707 V naught. We call these two things the root mean square. Okay? The root mean square. The average, and this is what actually is important for power. We know power, what's important for power is current squared and voltage squared. The average current squared is half the maximum current squared, and the average voltage squared is half the maximum voltage squared. If I take the square root of both of those, I get what we call the root mean square. The root mean square value. It helps us because the root mean square value can be directly utilized by the power relationship. So the power relationship that we've been talking about, P equal to IV, okay? The power relation that we've been talking to is, we can use the root mean square for AC in our power. When we do that, it behaves exactly, the device behaves exactly the same way as a direct current analysis using the root mean square values. Okay? So it takes all of our direct current stuff and we can utilize it we can utilize the AC material, the AC current. We can analyze that AC current by using root mean squared of those values in all of our direct current relationships. So there's a way for us to utilize the information and then to analyze the information. Okay, let's just do an example, and I think it might help. There's a lot of new equations and then using them in old ways and how we're justifying that. So let's do an example and see if that will help us out a little bit. So you know when you get a device, you get a power rating on that device. That power rating is based on the average, the root mean average values that, like, for example, we use here in the US. So it's based on the average. Now, because the average of current, in general, the average of the current or the average of the voltage would go to 0, the power actually is oscillating between those maximums and minimums, and so it is going through 0. There's a point in time when there's no power being dissipated by that device. We just don't notice it. We don't notice it because it's oscillating so fast. It's oscillating at 60 hertz. And so for typical usages, for typical devices like, let's say, a toaster, the example we're going to do with a hairdryer, those heating elements, which are dissipating that power, they're shifting between high power and low power, the plus maximum power to the minus maximum power, passing through 0, is happening, but it's so fast that the heating elements are certainly not cooling down before it's getting that high current, high voltage across it, and therefore dissipating high power again. However, in some applications, you do have to pay attention for it. In research labs, for example, where the electronics are very sensitive. So when I was a researcher in a neuroscience lab and we were looking at currents, very, 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 very small currents generated by the motion of an eye, we would sometimes see this weird undulating oscillation on top of our currents, and that was the 60 hertz of the lights in the room. So we had to figure out, how do we shield the lights in the room so we don't get this added oscillation on top of the signal that we were trying to study. So for most practical purposes, we don't have to worry about it. And for some purposes, we want to pay attention. So it's good to understand what is actually happening in our AC circuits. Okay, so let's do an example. See if that kind of helps flesh some things out, and then this little introduction will be complete. So let's calculate the resistance and, I should say, peak current. Let me just fix that because we don't like to have errors in our, I don't know what a P to current is, and I don't want people to be confused when they read it. So peak current in an 1875 watt hairdryer connected to a 120 volt AC line. Now, this would be a power rating you might read when you're going out to buy your hair dryers. And why did we, in the power unit, we talked about why we might want to be aware of some of that. Well, cost is associated with how much power is dissipated, how much energy is used for the amount of time that you're using that energy for, and you pay for that. So power ratings are important. So let's just look at this example. We have a power rating of 1875 watts, and the voltage, the AC voltage connected to an AC line, that voltage of 120 volts is given in root mean square. So that 120 volts is actually the root mean square value. That's what's provided with that information. All right, so the power is equal to the current times the voltage. That's our general power equation. We just learned that if I operate in root mean square, I can use this general power relationship. So the RMS current times the RMS voltage. The RMS current then is equal to the power divided by the RMS voltage. And so our current is 1875 over 120. So our current is 15.6 amps. So the RMS current drawn by this hairdryer is 15.6 amps. We know that according to Ohm's law, the resistance is the voltage over the current, and so that's the RMS voltage over the RMS current. So that equals 120 over 15.6, and our resistance is 7.7 ohms. So we can use RMS values to determine the resistance, for example, of this hairdryer. We also can use the regulars. Let's just kind of do a full example and see how this also compares to if I actually got I naught. So we also know that R is equal to V naught over I naught. Okay, that's from our original discussion of Ohm's law and then how it applied in the case here of our alternating current. So we need V naught and I naught. Well, I naught, I RMS value is equal to the square root of 2 times I naught, and V RMS is equal to the square root of 2 times V naught. All right, so, no. What am I doing? Oh, whoa. I am so sorry. That isn't what I mean. I is equal to I naught divided by the square root of 2. I did this totally backwards. I need to solve the other way. And V is equal to V naught over the square root of 2. We just did that. We just talked about that. This tells us that because I need I naught and V naught, I naught is equal to I times the square root of 2, and V naught is equal to V times the square root of 2. Much better. All All right, plugging in and this I and this V are, of course, our RMS values. Right? So 15.6 times the square root of 2, our I naught value is 22.1 amps. And 120, our root mean square value for the voltage times the square root of 2 is 170 volts. And so if we use those numbers, we get 170 over 22.1, and again, 7.7 ohms. So the resistance is independent of whether I'm using the root mean square values in my analysis or the peak values in my analysis. All right? We have to be consistent, of course, but this is just evidence and, again, suggestion and reality that the resistance is not influenced by this oscillation. Instead, it is a property that is the result of the product itself, and how we calculate it. We just want to be consistent with that. What else do we notice about this? Well, the 120 volts out of our household outlet is the RMS value of that 120 volts. The root means is the actual peak to peak is 170 volts. It's even a little bit higher. So understanding the rating of your devices is going to be pretty important. All right, so just quick introduction to DC and AC circuits, AC circuits in particular, and how they kind of differ between direct current circuits. And then just an example on using values of root mean square that we use when we analyze AC circuits and how they relate to the voltages and the currents themselves. All right, good job.